Okay, so the next idea that I think we should start for 10 to 15 minutes, or as you say, that is series. We can discuss what is series, and we can discuss two most important series, harmonic series and geometric series. Then we can take a break for 15 minutes, or if you say we can take break now, but let Ehsan Sahab reach here because we'll be having a tea break for that. Yes, inshallah. So what's the series? Series is what we call infinite sum. Series is infinite sum, or it's a special sequence. Is series a sequence?
Yes.
It's some sort of a special sequence.
Yes.
We can call a series a sequence in some other words.
Yes.
We are going for that.
Yes, sir.
But it's simply the infinite
What is
sum
this?
of all the terms in a sequence. We are not going mathematical, but we are talking about what does it mean basically. So for example, if we have this thing, it means that for this particular sequence, you have to add all the terms starting from the first term, that is 1, 2, 3, up to infinity, which is seemingly not possible because it increases and increases, and this sum is not finite. So we call this series to be not convergent.
Yes,
And then we define a notion, what do we mean by a series, to be divergent to positive infinity and divergent to negative infinity, but this is not convergent. I am writing some examples, but when you take this infinity to be a fixed value, then it I think converges to some sort of, what is the formula? N times n plus 1 divided by 2. If this n is fixed. If it is not fixed, then we can't do anything for that. Similarly, if I take n square, that is 1 square plus 2 square plus 3 square, this again diverges to positive infinity if we take the infinite sum, and we call this infinite sum to be series. Similarly, what about this 1 over n 1 to infinity, it is 1 plus 1 half plus 1 third and so on. This is also infinite series, or simply we call it series, and this also diverges. You know very well 1 upon n as a sequence converges to 0. But when you add these all the terms, this goes to, and this keeps on increasing, and this becomes infinite. And the next thing is that n equals 1 to infinity 1 over n square. That is 1 plus 1 upon 2 square plus 1 upon 3 square. This converges. But the problem is we are not always clear. We do not know always where does it converge. Or simply the thing is that what is the sum of this? What is the sum of all the terms in this series? But sometimes we have some special formulas that we can use, and this was found by I think Ramanujan, and he said that this thing is pi square by 6. 1 over n square, it converges, and the limit is pi square by 6. He found this limit.
Exactly or approximate?
Exactly.
Exact?
No, what do you mean by approximate?
Approximating of, because there is a irrational number divided
Yes.
by exact which is very good.
Exact. Exact. Yes, obviously these are rational, but the limit is irrational. And I think he found some other as well for the even powers of n, like n power 2, n power 4, n power 6 and so on. I don't know exactly whether it is even for odd, but this divergence is found for 2, for 4, for 6. But about odd numbers I don't know. Let me name this to be P. and n runs from 1 to infinity, and we call this function, I think, zeta function evaluated at p. This is the definition of
Special
I
function.
think special, but what is the name? Riemann zeta function or only zeta function? So let us name it zeta function only. So this is zeta. And when you evaluate this zeta at 2, means you put 2 here. So the sum is pi square by 6. When you evaluate zeta at 4, it means you put 1 over n power 4. And I don't know exactly, but that's something like pi power 4 over 90 or something else like that. But it is there. It is there. So these can be proved with some number theoretic formulas, or we have their proof in complex analysis using residue theorem or some other results. We have their proof. So these can be proved easily. I think some of these can be proved by Fourier series as well. You have Fourier expansion, and these can be proved with that. So these are some examples. What do we need in series? But we don't need these results. We only need that whether it is going to be, sum is going to be finite or infinite. Why do we need? Because when we expand a function in Taylor series, we always need whether that series converges or not. If it does not converge, then simply we are not okay with the that representation of the function. You have a function, you approximate in the sense of polynomials. Sometimes your function is not good for integration, so you replace with the polynomial. But if your polynomial diverges, then simply there is no sense to use it. You find series solution of differential equations. You have a series. If that series diverges, you are not okay with this. You only need to know that whether it converges or not. You need not to know what is the limit. What is the limit? It means what is the sum, what is the sum? No need to know. Only we need to know that whether it converges or diverges. So what happens? Let's say this is the sequence. Let me call it what we say n. N runs from 1 to infinity. This is 1 plus 2 plus 3 plus and so on. Now you take the first term, and I think you name it n equals 1 to 1 of n. Am I okay with this? Because you start n from 1 and n at 1, you only get one term.
Sorry.
If you need these two terms, you will write this n is equal to 1 to 2 n. And if you need these three terms, you will write sum n equals 1 to 3 n. So this is the sum of 1 terms, this is the sum 2 terms, sum of 3 terms, and so on. So at each and every step you have a sum of 1 term, sum of 2 terms, sum of 3 terms, and so on. So you generalize this notion by writing n is equal to 1 to k n. It means sum from 1 terms to some fixed k terms. We call this sequence a sequence of partial sums, and let us name this guy to be sk. And convergence of this series means convergence of this sequence of partial sums. Now this is no more a series. This is a sequence sk. S1 is the sum of only 1 term. S2 sum of 2 terms. S3 sum of 3 terms. Now you can apply each and every property of sequence to find out convergence in this case. So this is the idea behind this. If this sequence of partial sums converges to some fixed limit a, then this thing also converges. Now you apply the properties of the convergence of a sequence in this case.
This SK is the partial
Sequence of partial sums. Sequence.
सही
It's a sequence.
मिसाल वो पुरानो बेहतरीन मिसाल रोड मापनो आ तो सुठो अगर सिरे ई माप करे सको ता हिकड़ी रोड मापिंग सिरे ई माप नथा करे सको
That's the thing. That's the thing. But mathematician वाला से हम नहीं.
हां
वे हर जवाब का डंडा. It means they apply so many properties to do the things.
टेस्ट करावे जे टेस्ट एंड बटन एसयू कराशे ना पर
ये माना
रेशियो टेस्ट
ना उदाहरण कीजिए तो सीरीज में भी some sequences in which it is very easy to take convergence or divergence in some series. So we'll discuss those series first. The first example is, I think, geometric series. Geometric series. So it is the series of this form. Let's say there is some sort of ratio. Can I write n is equal to 0 to infinity? You know very well it is n naught. So n goes from 0 to infinity. We call this limit to be n naught. It's possible in sequences. Now this is a geometric series. When some fixed number, let's say q or a or b, is raised to power n, it means, first of all, I will give q power 0, which is 1, then q power 1, then q power 2, then q power 3, and so on. The question is whether it converges to a fixed limit a or not.
So
If it converges, what are the conditions for the convergence?
Q rational number हो जाए
No, it can be anything, but it should be some fixed value. Okay, so we need this thing. So what should be the value of k so that it is going to converge?
K less than Q.
We know very well, leave this to be k, q, write r. This is ratio, you know very well. And this thing is, this n is equal to 0 to infinity r power n converges if and only if less than 1 or less than or equal to 1.
Less or not equal.
Equal to would be the problem. If this is equal to 1, this is 1 plus 1 plus 1. You add ones, this diverges to positive infinity. So this is the condition for the convergence of a geometric series, and I think you know very well the formula for this one as well.
You are writing with
It's possible. So what is the limit? The limit of this or n as n goes to 0 to a fixed k, then you apply limit k goes to infinity, I think 1 over 1 minus r. 1 over 1 minus r. 1 is the first term, you can see. 1 minus r is what we call the common ratio. This is the formula for this. So this is the condition for the convergence of a geometric series. We should know this condition because these will be asked in so many exams. Does harmonic series converge? Number 2. Harmonic series. Then series of this form 1 over n, n equals 1 to infinity. It means 1 plus 1 upon plus 1 upon 3 plus 1 upon 4 and so on. So this diverges to positive infinity. This is the problem with this one. We can check the divergence. One way is to prove it. Another way is to apply some sort of test that we will be doing so far. And third way is to compute by using some sort of computer tools.
all harmonic series are divergent.
This is the special harmonic series. What are all harmonic series? Okay, 1 upon 2 and like this. They will diverge. They will diverge. Okay, so
yes, harmonic diverge नहीं है
yes, sir, it diverges to positive infinity. It means this does not converge. Diverges to positive infinity. That when does that converge and when not? So we have this one. Summation 1 over n runs from 1 to infinity, and this n raised to power p. When does it converge and when does it diverge? What should be the value of p? So there are two cases. it means this one converges if P is greater than 1. It means the value of P should be not 1 but greater than 1. Like the value of P is going to be 2 and 1 over n square. The value of P is going to be 3, 1 over n cube. It converges. 1 over n power 4, it converges, and so on. And this diverges if P is less or equal to 1. Equal to 1 means you get harmonic, and less than 1, let's say P is 0. Then what happens? P is 0. P is 0 in raised to 0, 1. 1 over 1, 1. It means you add 1 infinite times, it diverges. If P is minus 1, if P is minus 1, then this 1 over n power minus 1 becomes n, which is only natural numbers, and you add all the natural numbers, diverge. When P is minus 2, you know very well this happens, n square, which again diverges. So you have this criteria for the convergence and divergence. There is a criteria for the convergence as well, what we call Cauchy Criterion, and then we are going for some examples as well. There is a test called Divergence Test, which is also good to check divergence but not convergence. Let me write that test first. Divergence test. It's very good to check the divergence, not the convergence. Let me write in this another way. So an n equals 1 to infinity converges. If this series converges, it implies that limit n goes to infinity, n is 0. It means this is the series.
Yes, sir.
It converges. You take the general term of the sequence n. Its limit will be 0. If this converges, you can take this example. 1 over n square converges. What is limit n goes to infinity 1 over n square? The converse is not true. That's why I have written this. The converse is not true. Because you take this 1 upon n, its limit, this limit is 0, but it does not converge. So this is implication in this way. If this converges, then this happens. If this happens, then the series may or may not converge. You can see the things. Why it is called divergence test? Because when this does not happen, it means what I say, take the contrapositive, that when limit an is not equal to 0, then your series will not converge. Let's name this not convergence as diverges. This is the contrapositive.
Yes, sir.
When this limit is not 0, then your series is divergent. For example, this. What is this limit?
Infinity.
Infinity, not 0.
Yes, sir.
Just diverges.
Diverges.
What is this? 0
Yes, sir.
converges. Series diverges.
Series diverges.
What is the limit? 1.
1.
1. So it diverges. Does this diverge?
converge the theorem or not? According to this condition.
Does this diverge or not? This is the question. This diverges because
Diverges. One is that.
even this diverges because of 1 over n.
Yes, sir.
So this is the condition that you need to know. If this limit is not 0, then obviously this will diverge. Is this limit 0? Only check the limit of the sequence,
Not zero.
not 0. So this diverges. Always. If this is 0, then we can't say anything about convergence.
Convergence. Yes,
But
sir.
if it is not 0, then obviously it will diverge. This is the condition that we need to give. This is called divergence test.
सही अगर जरूरी कन्वर्ट करे तो वो सीक्वेंस अब 0 ते ही है
So जो sequence जेको जनरल टर्म आ उहो सीरीज जी सम न
समझना
उन जो जेको जनरल टर्म आ उहो 0 ते वींदो त केड़ी भी कन्वर्जेंट सीरीज खणो केड़ी भी कन्वर्जेंट सीरीज खणो
sin x upon x जो खणा हुआ लिमिट 0 होंगी छा होंगी
पहिरियां त सवाल इहो आहे त sin x upon x
उन पार्ट लिमिट
sin x upon x था खणो न पहिरियां जो सवाल हीअ आहे त तव्हां ही खणो sin n
एंड ये सही है
ठीक आहे हाणे पहिरियां असांजो सवाल इहो आहे whether this converges or not.
Yes, 0.
Sin n upon n. Mayam by it converges. What is the sum? There is some sum. This converges. It implies what happens. This must be 0. Is this 0 in this case?
If I'm taking limit, yes.
Take the limit of the general term only.
जनरल टर्म
Sin n over n as n goes to infinity. This is 0. We have done this by using sandwich theorem a few days back. Sin n over n when n goes to infinity. We are not saying when n goes to 0. Then this is equal to 1. We know very well. Sin x upon x as x goes to 0 is equal to 1. But this is when n goes to infinity equals 0. You can check this by checking the behavior of both as well. This behavior is finite. Minus 1, minus 1. And this, the behavior of n increases. 1, 2, 3, 4. So this n increases rapidly, so this would be 0. If this upper increases to infinity rapidly, then this limit would be infinity. If this increases rapidly to infinity, then this limit would be 0. So you can check the growth behavior of numerator as well as denominator. These are what we call the slowly increasing functions and fast increasing functions, slowly decreasing functions. So these are some types of functions that we can apply to take the limits easily. Like if I give you this thing, what happens? Limit n goes to infinity. E raised to n upon n. Now this particular function,
exponential
it increases exponentially and this increases linearly. So this increase is greater than this, hence it will diverge to positive infinity. Conversely, if I write this, so I am not checking anything, I am just telling you, okay, this will happen. N over e raised to power n. This will converge to 0.
all the एक सीरीज कन्वर्ज के डाइवर्ज के the sum
Yes, yes.
multiplication property होंगे
Within series के साथ compare
Compare करना।
भाई ये converge थी करे ये क्या करे ये diverge थी करे ये क्या करे. We can compare the things as
the
well.
sum multiplication
पर स्पीडी में चेक करणो आ त न्यूमेरेटर जो तमाम थी
Growth check. Numerator जी growth करनी है, so diverges to infinity. Denominator जी growth करनी है, it converges to 0. You can also check growth in sequences as well as functions. It's not only sequences. Functions में ऐसा check करना.
ग्रोथ त दिन में थे
Growth में नहीं, growth गणी कहीं नहीं दी. ये डिस्टेंस होता है खबर पड़ी. Okay, what is another criteria to check this? What we call Cauchy Criterion. Then we are going for series based like alternating series test, ratio test, and so on and so forth. This is the criteria that we should remember. We can use it in so many theorems, but at least for now we should keep it in our mind. What we call the Cauchy Criterion to check the convergence of a sequence. This is same as like to check that whether a sequence is Cauchy or not. So this is very much similar to that. So a sequence, let's say AK from K runs from 1 to infinity, is convergent if and only if what happens. For all epsilon, there exists some n in the set of natural numbers. Whenever you go beyond this n, the partial sums starting from m to n of your sequence can be made as small as epsilon. So this is the Cauchy criterion to check the convergence of a sequence. Like you say that this series is convergent if what happens after a large number of terms. This means after fixed n means you go after a large number of terms. You can take the sum of partial sum of your series from some fixed m to n. This can be made as small as possible, like less than epsilon. So this is a criteria to check the convergence, and this criteria can be applied to check the convergence or prove different results, like alternating series test. There is a test but there is a proof for that. There is a ratio test but there is a proof for that. We can apply these criteria to see that. But why is that so? This is similar to Cauchy sequence. You know very well you can approximate this by sequence of partial sums, and that sequence is called Cauchy. Then when what happens? When you have some Sn terms minus Sn terms can be made as small as possible. This is the property for, you know very well, Cauchy sequence. When the difference between two terms can be made as small as possible. So these partial sums can be rewritten in the form of the sequence. It's easy to do this, or it's easy to check this particular thing. Okay, we are taking a short break for 15 minutes, and then we'll resume after 15 to 20 minutes. It's 12:33. We'll resume at 12:50 and discuss the remaining things that we need to.